All right, I think we're good. Dude, why does my streamer bot just work when it feels like it? Like, I don't understand you. It worked the other day, and then it didn't work, and then it's still not working, and I didn't change anything. There. Okay. What's this Fourier cosine? Bruh. What was I doing with this problem? So first I found the equation for the Fourier cosine transform for a second derivative. Then I used it right here. Then this is a first order differential equation, ordinary differential equation in time. Do they give us phi prime? Ooh. Okay, yeah, prime. Yeah, so we can use this condition here. It's just g of t. I do have a feeling that why is there a minus? Wait. Hey, fun case. I'm trying. I hope you're doing well. Um, I'm basically trying to get a particular solution for the heat equation, which is a thing in math that can describe how heat spreads throughout some like metal object. It's pretty it's not easy though. Got my spell book out. um okay, yeah. So this minus sign is the same as that minus sign. That's funny. There actually is a streamer called Math Spellbook who has that like theme for his math stream. He's a good guy too. You were an iron worker, you know, intuitively thermodynamics. I can express it into numbers. That's fair, yeah. I bet stuff like this is in the background of what you're doing, not that you'd really like need to know it. It's kind of weird. It's like uh, I'm saying this from like a math angle where we don't really care about applications. This is like one way you could apply it, but like Joseph, congrats on the first. But the same equation, like we call it the heat equation, but it's also called like the diffusion equation, and you can use it to describe a lot more situations than just heat spreading through a rod. It could be I think it can describe how like gas spreads throughout a room and stuff like that. If you have like clustered off in a corner and then you suddenly like release it, I think. I think I'm already going wrong. I feel like this book loves to bring in the Dirac delta function. And I feel like I probably am expected to do that here. The light and frost effect. That's how slide doesn't burn into your arm. Because heat makes steam. Oh, maybe I might have, I haven't heard about that name, but I might have heard of that. Interesting. A tract about some qualities of common water. What a mundane name for presumably a book. Something hot, bouncing stuff. Yeah, I feel like I've heard of this. Maybe in this like cooking context where you can use water to test if a pan is hot enough. Ooh, this is gonna be cool, I think. Ooh, you can see there's like an air bubble there. That's cool. I wonder if it takes longer for the metal to cool down because there's, I guess, okay, see, now I assume they've lost the effect because the temperature's gotten close enough together. Huh. Man, this, the dude has a totally straight face. He's maybe got a slight smirk now. Culinary is the international, it really is the international language. Oh my god, there's so many videos. Oh, this is the cooking one, I guess. That's kind of a just a weird one. Ooh, it's like a Beyblade. Look at that thing go. This is a good like loading screen in a video game. So it'll be very random. Oh, what are they about to do? Adding more water? That's not the type of water that you want to drink. I was imagining a person on the other side of the straw just like sucking the water in. That's probably a pipette, to be honest. That's probably not a straw. That will make a lot more sense. Ooh, this might be the answer to the question that I had. I don't really know what this is saying actually. Rate of heat transfer, temperature of pan above TS. No, I don't quite know what they're saying there. Anyway. Oh, that's right. I was looking for where's the example where they use the Fourier cosine transform? They did one, or maybe it's the Fourier sine. Either way, it's going to be helpful to look at. Here we go. Hey, Skirtle. We doing well? Okay, this do squared, it's do. Because you're do. Oh, right. Er. Mm. I think they're doing a convolution with the homogeneous solution here. I think that's where this equation comes from. So I guess let's try that. If your body's X% water, something above the boiling point can't burn it into it because it is levitating on the steam it makes. How's the guy who held stuff in place as it got welded? Oh, no. I guess, yeah, you would be the person who would know that, I guess. I can't imagine that's safe still, but that probably reduces some of the harm. Yeah, great comfort to know that. Okay, so now we consider the homogeneous. Oop, forgot to give that phi its hat. Came in for the banging flute solo just then? Oh, yeah. It is a banger, this song. Every day's been good, Phobos. Okay, so what are we doing here? We're doing something. It's been a day? That's much better than it not being a day, let me tell you. I think we're just gonna get rid of this. You know, I kind of regret subtracting this to their side, or like this to their side. How not was my day? My day was not bad. There we go. Or it definitely was not a day. X fret. It's applied math, I guess. I'm trying to solve the heat equation, which, you know, it is physics, but mathematicians study this too. Oh shoot! You started it on your master's program by now, right? How's that going? Using only the word "not" rate your day. Not. I don't know how many times I said "not," but finishing my bachelor's. Oh, okay. Hell yeah! I just had my first day of class. I just remembered half of it that you were going back to school at least. Um, that's awesome. I just had my first day of class for my master's yesterday. So that's funny. We started just around the same time. Yeah. We haven't learned much yet, so I sure hope so. The uh all I've covered is like Euler's method for differential equations for like getting approximate solutions, which is something that like you learn in like your first differential equations class, and then in my applied complex variables class we just learned like Euler's formulas and stuff like that. So it's nothing crazy yet. I'm gonna have to do stuff like this though by the end of my complex variables class, so I'm practicing it now. It's been pretty emotional for me since it's been so long and finally back. Hard to believe. That's fair. I have been having a lot of anxiety about it, about like going back to school too. It's been a while for me. But yeah, I like in terms of the emotions at least. The first day is the hardest, so I'm glad that you got through it, and hopefully you'll be like more settled in now. Hey, Catmaster. Hope you're doing well. Oh, good emotions. Okay. Approaching, I could be ready to come back. That's fair. So basically, all the issues are holding me up before. Oh, fantastic news. So anxious though. Who knows what the future will hold? Yeah. That's how life gets you. Thank you. I'm working on the part A for the Fourier cosine transform. And the way this book's been solving PDEs is very strange to me, at least. I don't know if it's conventional or not, but in one of these NCL problems I was looking at, they said, okay, we'll start with solving the homogeneous version of this problem, and then they do that. They never get back to the particular solution at the end. And I was like, well, we can't just ignore that, can we? A year and a half ago, I went from thinking I was going to get married in 3 months to moving 2,000 miles away back to my parents. Oh, geez. That's a big change. Oh, yeah, that's awesome that you're, I guess, like, getting back on track and pursuing the things that you want to pursue. It's a standard method. Students will figure it out after the homogeneous part, maybe. The good news is that, this is the main book that I've been following, and this is the main book that the class uses. But there are, like, there's also lecture notes that I now have, and there's also an unpublished book that the professor wrote that I also have now. So I need to take a look through those and see if they solve these PDEs also in a more understandable way. They also recommended a third actual textbook that's supposed to be more rigorous. That might, I mean, I don't know if they will show more steps, but it's at least another resource that I can, like, look into. Okay. So this is just a first order equation, so we only get the one solution. We can apply our initial condition. That bad boy. I think it just means that A of k is going to be 1. Wait. Does that mean A of k is 0? Am I stupid? Am I playing it too soon? It's like, or should I try to untransform it first? Oh, yeah, no, I shouldn't apply initial conditions when I've only done the homogeneous part. That's it. Need to wait until we get the particular. And for reasons that I don't quite understand, where's the actual... Okay, yeah, so yeah. Okay, for reasons that I don't quite understand, we use convolution to combine the homogeneous with the particular solution, rather than just doing the thing that I'm used to with doing homogeneous plus particular. What shouldn't we have a k? Shouldn't this be k cubed and not just k? Hey, negative plasma. Your sister swims out to meet troop ships? What? What does that mean? What type of fortune is that? Is that a quote from something? Is that an AI hallucination? It's from a song? What's good? Life, you know? Hope we doing well. What a random why would you make that a fortune? Color cone. The hard times will begin to fade. Joy will take their place. That's a nice fortune. It's cheerful. Oh wow, there's Reddit posts about this. Just seems like a waste of energy. Okay, this is a stupid thread. So what they're doing, they're solving the homogeneous version of this differential equation. And they should be getting, what's from the initial condition? What's their initial condition? No initial condition yet. Oh wait, what would the other term be? I don't get it. Oh, I can see where it come from with the integrating factor. But I don't see... FA, they are. Thank you. The two professors that I've met so far seem like pretty nice. So, well, one of them, like, I was supposed to have, or my third class yesterday got canceled, so that one's not going to meet again until Monday, but as for the two that I've seen, they seem pretty cool so far. I say hi to you, Central, but I know you're talking to yourself. Hey, Rex. Tiny hands rule. All you oh, well, that's very kind of you. And if I hope your internet issues get resolved. Looking extra ginger today. Well, thank you. You like Reddits? Ooh. I've seen you on that Nihime and BR grind. BR is so fun. I've seen it has kind of long wait times though. But I do see that they've really like overhauled it and made it a lot better. I haven't tried it for myself yet though. You have one ginger hair in my beard? In your beard? You know, that's good enough for me, Carla Cone. I'm calling you a ginger. It's hot. Zach, it's been good. I the two classes that I've had so far, scientific computing and applied complex analysis, seem cool. Both the professors seem nice. And apparently for the one for applied complex analysis, like, you know, the class was supposed to be the hardest one. I got lucky with the professor where it could have been a much harsher professor. I think they like trade off years of teaching it or something. And I got the easier grader. But I just really like his like philosophy too. With he's focusing a lot on like the applications, or he said he will, and he's gonna skip like the proofs or stuff unless they're really relevant. Got lucky with the professor already. You move fast. Shut up. But yeah, and so the math bio class, I was it was supposed to happen yesterday, but it got canceled because the professor, I guess they need to get a new one for some reason. For some reason that they didn't explain. So I'm not gonna have that class until Monday. But yeah. And then just today I didn't have any classes today, but there's like a grad student like panel where they got a bunch of grad students to like help answer questions for they got a bunch of experienced grad students to answer questions for the new grad students. My beard is like 60% white and silver these days. I mean, that look can be cool too. Yeah, negative positive. Complex analysis is this book that I'm reading from right now. I'm trying to learn PDEs from it. PD teacher didn't show up to half the lectures? What the hell? Like, did the TA do everything or what? Oh god, there's a bunch of fortunes. We give up leisure in order that we may have leisure, just as we go to war in order that we may have peace. Oh, okay. I think I understand that, yeah. You will step on the night soil of many countries. That's a weird way of saying it, but Skirtle has traveled a lot. But isn't night soil another word for poop? I don't know. Your artistic talents win the approval and applause of others. Ooh, Zach. Okay. You have literary talent that you should take pains to develop. The pains part is a little weird. But you do have literary talent, Rex. Rod13, thank you for the follow. Okay, look for a priceless bit of news from a loved one. Ooh, okay. Hey, Rod, welcome in. Can't go wrong with Rudin. Oh yeah, that's like the really difficult analysis book though, right? This book is way more applied. It's not very theoretical. I'm brushing up with Horn on matrix analysis and operator theory for my postdoc research. Oh, nice. Program for tomorrow, taking care of kids, figuring out new things about linear operators. Noish. How do we ban this person? I got a button. It's really easy. That phone message? Yeah, it's a thing. It's a little clip that Dr. Cook showed me a while back. Oh, good, I'm hungry. Hey, Geody. Even Central knows the Mommy Milkies thing. Scriddle makes everyone say that. No, she makes me say Mommy Milkies all the time too. Whenever I ask her for a favor, it's just funny to see that she makes you do it too. For 3 years, okay. Everyone just says it without protest. Yeah, I know I'm not special, as much as I hope. Wow, you've been doing Central for 3 years? That's gross. I'm doing good, Geody. Thanks for asking. How about you? What does Milky mean? It's Mommy Milkies, you know? Been looking at the connection between singular values and norm of an operator. I wanted to understand what the norm of an operator means practically. Oh, I remember you talking about that on stream. So you have some rabbit holing to do. Fair enough. Okay, down one day we'll sit you down for the birds and the bees thing. Thank God. I've just been playing it off like I know how that works. The quadratic formula? Yeah, I can show you it. I don't know if you want anything special, but like some videos. Oh no. So like I'll show you how to play, but like tell me if you want to see something else with it. Like so if you have 2x squared plus 3x plus 5, let's say, equals 0. Well, I guess let me show you the generic version too. With just like, if we make these constants instead of actual numbers. You wrote directed and started them all. Defiled my chat. Yeah. Thank you, Skirtle, for defiling my chat. Enjoy your... I assume you're once humaning. You're going to people talk now. Alright. See you both. Enjoy. Okay, so... the general quadratic formula is x equals minus b plus or minus square root b squared minus 4ac over 2a. You just need to memorize this, unfortunately. Milky Bar? I don't think I've heard of that. If a is greater than 1? I don't know what... Oh, I don't know what CTS formula is. The quadratic formula works for anything with the square, though. Center of square? Oh, maybe like completing the square. Yeah, if a is 1, you could do that too. But it like the quadratic formula, it does just always work. You can use it for any quadratic you want. That's the nice thing about it. So if I apply this formula over here, basically a is 2, b is 3, c is 5. So plugging things in, we get x equals minus 3 plus or minus square root 3 squared minus 4 times 2 times 5 all over 2 times 2. Bring the formula easy to remember. Oh, good, good. This is a good one to have memorized. You got a C streak? A 5 streak? Wait, I don't get it. It works for any field where 2 is invertible Oh, C is ah. I feel you, Jed, now. Where 2 is invertible and square root b squared minus 4ac exists. There you go. Yeah, Nishu, we can talk about that in a second. So from here, it's just a matter of doing math now. So, or like arithmetic. So 9 minus, oh, I didn't choose, I chose one with imaginary numbers, maybe it's in the best first example to show. For 4, I just made up random numbers here. So we're getting weird result. No homework yet. I need to set up a programming environment in Python. That's the only thing that I have to do right now as far as I know. I will have to LaTeX up my solutions for the complex class though. They recommend that you do. Yeah, so GOD, it sounds like you know what to do. When you get a negative square root, we just bring it out as an imaginary number. And so this is basically your answer here. If you want, you can split them out based on the plus and minus. 3 plus I root 31 over 4 minus 3 minus I root 31 over 4. If C is negative 5, you get nice roots. Oh wait, we don't get a 69 though. They are nicer though, right? 2x2 matrix using inverse method / Kramer's rule. Yeah, it's been a minute since I've used Kramer's rule, but I think those are two different things. So which one do you want to see? Should use an anti-streak sense for the previous 5 streams. Inverse? Okay. Can you put the I outside the root on the other side? Oh, like over here, you can do that. It's just if you're sloppy with your handwriting, you might accidentally make the square root go too far, and it might look like the I is underneath the square root, which is a different thing. So I tend to write them in front, but you could put it after. Mathematically, that's fine too. Just make sure you're careful with like how far the square root bar goes out. It's the same thing though. So yeah, Anish, we can talk about. So I'm interpreting your question as you have something like GOD. It's really just the same thing. Like there's nothing new to do here, and I want to answer Anish's question. But it's really just plug numbers into this. I'd encourage you to try it for yourself here. No, it's all good. I just want to make sure that I can get to a niche in a good amount of time too. Yeah, you just change the numbers exactly. So Anish, I'm interpreting your question as you have something like AX equals B, and you want to solve it using inverse matrices. All right, see a GOD. And so to give an example of what I mean by this, let's say you have like 2, -1, 0, 5 times xy equals 3. I might be sabotaging myself with these with these numbers, but like are you trying to solve an equation that looks like this, Anish? "12 bananas." What is this? Can you classify all real matrices up to conjugation of size 4x4 that satisfy? Maybe? I probably can't. Yep. Okay. So the idea with inverse matrices is that as long as A is invertible, we can left multiply each side of this equation up here by A inverse. Because we want to solve for x here. So that's how we can isolate x. And so A inverse times A is just the identity, which is basically 1. So we get X equals A inverse B. So it's kind of a question they like to ask in the qual exam. Oh no. So it's not like you're not allowed to divide by A because A is a matrix. In matrices don't have division defined for them. We call it multiplying by the inverse instead. It accomplishes the same thing, but it's slightly different. No worries. And so how we can do this down here is this is our matrix A here, so we should find its inverse. And luckily for 2x2s, they have a... Oh, I didn't respond to the other chat, Zach. You could have said vinculum, because it's just a fun word. I haven't heard of that word. So if we want to invert this matrix here, they have a nice pattern you can always follow for 2x2s. Someone gives Zach an oblate spheroid dotted with particles of theobroma cacao. I'll give you the general formula too in case you haven't seen it. If you have a matrix A, B, C, D, the inverse is 1 over the determinant, AD minus BC, times you switch these two entries here, and you negate these two entries here. And that always works for 2x2s. Unless you get a 0 here, then it's not invertible. I think you want me to have a chocolate chip cookie. Oh, okay, okay. Carl Cohen's a grad student. Rex. Or sorry if that was obvious. I don't know. So if I do, so if I apply the formula here, it's 1 over 2 times 5 minus 0 times negative 1. And then we switch these two. Negate those two. We have a negative 0. No, we don't. And now let's just clean this up. So this is 1 over 10. And oh, this is a 0 times 1, so it just goes away. Put the 12 bananas at songs in my stream intro. I'll watch it right after this problem. No worries, Anish. I'm gonna take the 1 over 10. You don't have to do this, but I'm gonna multiply it into all of the entries in this matrix. You could leave it outside if you wanted. But that's what you get. So what we can do now, I wouldn't normally write this entire thing out if I was doing this personally, but just to show you what we're actually doing here. We're taking this equation, we're multiplying on the left of each side by the inverse that we just found. And so we already know that this is just the matrix I. If you want, you could like do that multiplication and verify it, but it's just going to result in 1, 0, 0, 1. It's not necessarily like the determinant is involved. The thing we're multiplying by is the inverse matrix, but we do find the determinant on the way to finding the inverse matrix. Did you make a new account? Has been single whole life with a 1 instead of an L? Hello again, though. Okay, and then now we have some multiplication to do here. The 3 and the -1. Oh, that I just made that up as part of the problem. This is just whatever vector's on the right-hand side. Alt account, fair enough. I think you have seen this voodoo before. Yeah. So this is a 2x2 and a 2x1. So the result is going to be 2x1. We're going to take that column times that row and add them up. So 3/2, I need more room. -1/10. Then this column times that row. 0 -1/5. Now we just got some cleaning up to do. XY times the identity matrix is just XY. And then 3/2 -1/10, mental math. 14/10, which is 7/5. And -1/5. And that's our answer. XY is 7/5 -1/5. Make no rash moves for now. Ooh, play it safe, Jed. What's the purpose of using inverse matrices? Well, they're cool because you might be in a situation where you're trying to we're like we now have an easy way to solve a matrix equation like this, but for any vector here. Like all we need to do is multiply it by the inverse. So like if I randomly change these numbers to like 5, 12, I could skip straight to multiplying by the inverse and get a new answer. So that's like the nice thing about this inverse matrix method. It makes it really quick to solve other problems too. What's this 12 Bananas song? Yeah, Niche. Thank you for the question. If it was algebraically expressed, it would be exactly, yeah. So I can make a problem exactly like this if I say 2x minus y equals 3 and 5y equals -1. This you could solve the system of equations just using like substitution and elimination, and you would get the exact same answer. Like these two things are completely equivalent. But the cool thing with inverse matrices is that, like, again, like if you had this system of equations, it'd be really annoying to solve it if I suddenly change that to a 4. But with inverse matrices, it'd be no problem. You just do a little bit of multiplication. If you can solve 3 by 3 matrix, what if it's like 10 by 10? Well, then you use a computer. Because matrices get very tedious very quickly. The same technique would work, it just you wouldn't do it by hand anymore. Or at least you at the very least do some row operations. As for 3 by 3 matrices using Cramer's rule, I know to solve it. Is there a pattern? I don't think there's a way to simplify it. You just kind of have to do it, unfortunately. I haven't done Kramer's rule in a second. Oh, yeah, yeah. No, I don't think you can make this go quicker, as far as I know. You could probably do row operations first and get some easier to calculate determinants. Uh, but I don't think there's any like tricks to it. It's general form to write the inverse matrix using Kramer rule, but it's very annoying. Yeah. Is that the same thing as the cofactor stuff? It is? Okay, yeah, yeah. What game is this from? Banana game? That would make sense. The new Donkey Kong? Oh, that's so perfect. It is a banger. So is Coconut Song? Is it from the same game? No? Does it? I don't hear that accent. Well, maybe. What is the Coconut Song? Yeah, Anish, that's how you do it. Is the entire song going to be like this? No? I kind of love this song. Anisha, it's kind of hard for me to answer because I don't know what your Algebra 2 class is going to cover. It's kind of different depending on the place. Okay. I think it's enough of the coconut song. I'm not sure it's computationally possible to use Kramer's rule for a 10 by 10 matrix generally. Determine a computation frame by and matrix requires. Yeah, I think computers would do row reductions first. And then they probably are going to do some tricks after that. My favorite application of Kramer's rule is to say the map from A to A inverse is smooth or regular. I guess I don't know what smooth or regular means, but I mean, that I feel like non-invertible matrices would throw a wrench in that? Question mark? Unless you narrow it down to invertible. I had a joke about coconut as it is the only tree which enjoys people sucking his nuts, especially coconut drink. Geometry, we had to map out our proofs over a whole page, draw like arrow marks, different properties to get the final answer. Oh, I didn't have to do exactly that for my geometry class, but I did. They did give us these annoying tables, and we had to fill in like partially filled steps and justify each step with like a theorem. It was annoying. Raining tacos or breakfast burrito? Neither. Ten seconds of each and you'll get the gist. Okay. 93 million. This does feel like a 2012 type of thing. Oh my god. Rest in peace my YouTube recommendations after this. This person is not a fan of comments. And I think that they're right. You always sing this song when they're ready? Nice. I love it. See, I feel like it's a burrito with its brain spilling out. That should be closed up on that side. Oh my god. That's all I can take of those songs. That is awesome that you sing that for your kids, though. You're sharing yourself to GL. Oh, okay. That does it. Makes sense to ask for to be smooth in the sense of multivariate calculus. I didn't think you could ask for that to be smooth in the sense of multivariate calculus, but I'll believe you. That sounds like a topology thing. I don't know if it is, but... What was I doing with this? Oh yeah, I was trying to figure out how the hell the book was solving a first order differential equation. You can do some cool tricks with that? Okay. So should I just let's just do the integrating factor thing. So I'm no longer sure that they did the homogeneous non-homogeneous thing. Ooh. Yeah. Do they say the word homogeneous? Let me just... Okay. No, let's try integrating factor. So the integrating factor e to the k squared t. I think this might be the term that gets dropped out when we apply the initial condition. Do you know the annoying proof of Cayley-Hamilton using the adjugate matrix? No, I never learned the Cayley-Hamilton, to be honest. I've learned it from Slimstream, which is a matrix satisfies its own characteristic equation or something. Yeah. Usual proof in most textbooks is kind of tricky. You have to have some random computation. Oh. Vito only proves it up to 2 by 2. Thank God they proved the 1 by 1 case. Okay, here's a real proof. Using the garbage of topology, you can reduce to the case where your matrix is diagonalizable. Is that this Jordan normal form idea? Jordan normal's kind of cheating? Oh, okay. Oh, I'm not reading all this. I think this was their... Oh no, this wasn't even... This is just preliminaries. Okay, yeah. I'm not going to try to understand this, at least not right now. So you'll have to give a very annoying proof of Jordan canonical form without using Cayley-Hamilton. Oh, okay, okay. You got cooked in your test? Oh no, Art. I'm sorry to hear that. This is a really in-depth Wikipedia page. I feel like this one is a lot kinder to the reader than most Wikipedia pages are, without having actually read it and only skimming it. A bogus proof? Oh, that's my favorite type of proof. Substitute A for lambda? I don't know about that one, buddy. There are many ways to see this argument is wrong. P of A is an n by n matrix. Or the right-hand side of the equation is just the value of the determinant, which is a scalar. It's going to be equated unless n equals 1. The variable lambda actually occurs at the diagonal entries of the matrix. Okay. Oh yeah, what the hell is happening there? Oh my god. Apparently, color code, that message has something to do with race, ethnicity, or religion. Automod is back. Dude, when I first started streaming, my Automod was holding up math comments all the time, thinking that it was like bullying or something, and it's back to doing that now, it seems. To the kids n equals 1, GG. Keep your race, religion, and ethnicity out of this color cone. You had a big warning screen before sending it? Oh my god. That warning screen scares me so much whenever I get it. Even if I'm saying something that's completely fine. Math, I prepared so good I have the worst teacher. He puts question he doesn't even prepare us for. Oh, that sucks, Art. When do you start learning proofs, or is that a math major thing? That's normally like a discrete math or real analysis thing. That's where the proofs really start to like come in. Sometimes with like a more advanced geometry class, maybe. But those are the areas that come to mind. Art. Hey, math fanboy. I was just happen to be looking at a linear algebra page right now because we're talking about it. The thing I'm actually studying when I'm not running my mouth is applied complex analysis and like partial differential equations. But we started to talk about the Cayley-Hamilton theorem. Religion is a base case of induction when n equals 1. You like number theory? Oh, nice. I gotta say, it's not my favorite area of math by a long shot, but it does have its uses. So yeah, what I'm trying or what I've been kind of doing in the background, math fanboy, is this problem here. Solve the heat equation with these initial boundary conditions using the Fourier cosine transform. Number theory does have its uses. Hardy would be horrified to hear that. I know. Ugh. We do need the type of mathematician who hates applications, but God, I just don't understand that mentality. I just watched a Veritasium video about Markov chains, and Markov was like one of those dudes who specifically does not want anything to do with applications, only does pure math for math's sake. And he invented Markov chains just to stick it to some other mathematician who he hated, and then never did anything with him again. And he literally wrote, as to the uses of it, like, I don't care or something. I'm only concerned with pure math or something. He literally like explicitly said that. He did math the same way some do poetry. That's a nice way of saying it. Okay, so what happens here? So somehow I need to magically change this to be convolution. I don't know how. But what if I worry about the initial condition first? We're getting minus integral g of 0 dt plus a of k equals 0. Well, do I need another constant here? No, I don't think I do. Because a of k is my constant. Well, this is stupid. No, I did something wrong here. Ah. So the annoying thing, one of the annoying things here is how do I get the bounds of the integral? And how do I get t prime in the mix here? I also forgot something. Did I? No, I didn't. Okay, well, let's back up even farther. So let's just do integrating factor by hand here. So we would need to require that mu prime is equal to mu k squared, which would imply that mu is equal to e to the k squared t, which means v hat c is equal to a minus mu g of t. So what I want, the reason I'm doing this by hand is that I now want to integrate from 0 to some other thing. Does the fundamental theorem of calculus still give me this cancellation? I should know this. It's just the... Well, wait, okay, let me write out what I'm trying to do properly here. Let's say from 0 to c. Hmm. Uh, this is stupid. I'm getting these c's in here, which is just a dummy variable, but like... Is it gonna become my t prime, maybe? I don't know. Oh, you know, I should turn my background lights on. Probably dark enough. Let there be light. You can kind of see them. Which one do we want? What scene? Morning. Ooh. Let's do that. Let's do morning in the evening. This is getting... This is getting a little bit stupid, but let's just see where it goes. Can we somehow pull something out of our ass to make this work? So this is phi, not I. Wait. Oh. Well, yours... Okay. You're 0, good sir. I don't know if anyone told you that. Uh... I know what mu is. Why did I still write mu? Wait, oh, maybe this does work. Once I rename some things. Because this has nothing to do with T. It can come inside. Come inside the integral. Yeah. And we can rename variables. It's a thing that's allowed in life. Do an old switcheroo here. Anish, this is it's called a partial differential equation that I'm trying to solve. This is a lot to just like kind of drop in on, I guess. So we could say, we could put a minus out front, transfer the prime on that one. Just make it look more like a convolution. Okay, I think, but with great difficulty, I think I've gotten to where the book has gotten. They really skip over a lot of stuff from here to here. And now we just apply the inverse transform. Two over pi, cosine kx, 0 to infinity. This is for an applied complex analysis class. And it's like graduate level math, I would say. About IB versus AP. I've only taken AP. I've never done IB. I think IB is more internationally accepted though. Depending what kind of it probably just depends on like the type of university you want to go to, which one is right for you. But if you want to keep your options open in terms of like universities outside of wherever you're from, or just like universities around the world, IB might be better. Hey Jay, I don't really have an email that's like that. If you want, you can try putting it in Discord. UCSD. Oh, nice. Yeah, I mean, in that case, you could look at I'm sure UCSD has a page on AP classes in IB. Oh yeah, look at this. So I look at which classes are available to you and see what'll potentially get you more credits. Or if they're the same thing, go by like who the teacher is, maybe. Yeah, I think this is the best page to take a look at. Do they change the order of integration here? Integrate by parts. Why is the DK there? I hate that. They do interchange integrals. That doesn't fuck up your bounds? Oh, I guess you don't have to worry about it when they're sort of constants. I don't know. Yeah, I guess they're constants, so you don't have to worry about changing the bounds. What I'm asking is, we took... Oh, could you explain how F inverse B1 intersect B2? It's a subset of F inverse B1 intersect F inverse B2. Uh... Set theory isn't my strongest area, but let's see what we can do. Uh, I don't understand this half of what you've written. Or I don't know what the first and second cases are, really, but... Oops. But this thread might address the question. If A is an element of F inverse of B, then by definition, F of A is a property of B, or it's an element of B. Well, yeah, I I don't think there. And what I'm reading here, there aren't any cases though. I'm not sure why you need cases for this problem. But like, I think this proof would do the question, and you really don't need cases for it. So yeah, I'm sorry, Jason. I don't understand the exact thing you're asking about, but the proof that's on this page seems good to me, at least. So if cosine is equal to e to the kx plus e to the minus kx over 2, um, I like it Jason, I just don't understand what you're talking about with cases. Like, if you want, you can post it in the Discord server, but please don't DM me directly. I would honestly just use the proof in the link. It's much easier than anything involving cases. It's especially hard to understand your question when I don't really know what your cases are. Hey, Sage. Hope you're doing well. Yeah, just how it worked out for me today. My streams will probably be more around this time of day. Parents on vacation for a week at the house mostly to myself. Nice. That's awesome, Sage. Yeah, JSM, that might help if you can post it in the server. Get back to a nice empty house about to eat Chinese food. Hell yeah. Chinese food sounds great. Okay, see you, JSM. Please just post in the server instead, though. Please don't DM me. Ooh, I forgot the eyes. It didn't cross my T's or dot my I's. Wait. Integration by parts. Wait, what the hell are they saying? By integration, we can show that and integrate by parts. What? What does this say? Like, what does this mean? Wait, this isn't even true. Wait, where's the I? Oh, wait, oh, the parentheses. By integration, we can show that this. Integrate by parts. 4.6.12. Oh. Like a Green's function. God, this is hard. Um, So what are they doing from this J function is a little bit out of the blue. I think they're maybe just not explaining what's happening all that well. They're interchanging integrals first and then integrating in K. But they have this weird J intermediary that they just kind of... They don't technically need, since we know what J is right here. But this is the thing they're integrating by parts, I guess. So I'm going to interchange integrals, I guess. G of t prime can go there. You don't integrate this by... what? What? I feel like they're not actually integrating this by parts. Uh, so basically how this book is doing like 5 steps in one. I'm trying to understand like basically this section here. And I'm concerned that they did something wrong because they forgot the I in the denominator of sine here. And I hope that the typo didn't bleed through to the actual work in these steps. But I think they took this double integral, switched the order, and just worried about basically this integral here. Oh wait, maybe they integrated that by parts. Oh, maybe I understand what they did now. They have this k in front that I don't have. Yeah, integration parts would help you out with that k. And the problem I'm doing, there is no such k though. So I think I'm okay. Haha. Okay. Why use T prime? They love a good T prime. And they also love having functions of T minus T prime. It's the one they like to use for convolution. I don't know why. It does? Okay. I'm still very sketchy on convolution. Hey, Bread God. So I think that they're trying to make it look like a convolution. Although I think it didn't necessarily come from one. I think they massaged it so it would end up like one. And I'm trying to kind of mirror that. Oh, this is so annoying. So I want to do this integral here, but that I ruins everything. What can I do about it? Uh, these eyes, I guess. Shane, thank you so much for the raid. Adventure. I hope your stream was good. Lopta, welcome in. Eris, hey, welcome in. Ivan, hello. Brittany, hello. Holy crap. Uncle Bill, Matt. Welcome in, everyone. How many bits to lie tangent to my curves? For you, only 2 bits. Hey, Silver. Welcome in, everyone. Birdie, hey. Thank you. Chocolate Men's, hey. For anyone who's new here, my name is Don. The thing of my stream is I basically take people's math questions from chat and I answer them as best I can. When there are questions from chat, I just kind of pull my own things to study, and I like to torture myself with something called partial differential equations. This one is called the heat equation. It can describe, like, if you have a metal rod and you heat up one end, the heat equation can describe how that heat kind of permeates throughout the rod. And it's kind of gnarly to solve, but I'm studying it because I am a new master's student studying applied math. My first day of class was actually just yesterday, and this is something I'm gonna have to be able to do by the end of the quarter here. Hot rods, yeah. Thank you, Eris. And for anyone who's here on my end, you should check out Shane. Awesome streamer. History, sociology, building Gundams, all that stuff. I did listen to the first like couple of minutes of your stream, Shane. I hope that you get some rest. I wasn't able to catch much before I went live myself, though. Thank you, Ivan. Yeah, it's about the Enlightenment, right? I think I'd only just heard about whoever invented utilitarianism. That was the last thing that I heard. Oh, Zach, you were over there? Oh shoot, I didn't think they were follows. Birdie, thank you for the follow. Chocolate Mints, thank you for the follow. Um, yeah, I feel like I'm forgetting something that I should be saying, but hopefully not. Um, and for those who are new, I don't just do disgusting looking math like this all the time. It's just what I do when someone is asking me about something else. But if people want to talk about why 2 plus 2 equals 4, I will happily talk about that too. Hey, Papadoria. Uh, Berude, hello. This is math. At first, I thought it was disgusting looking philosophy. Thank you for the follow. Yeah, if this is philosophy, be some messed up type of philosophy. I was just reading, or no, I wasn't reading. I saw a video about how a philosopher, a mathematician, thought he proved free will with math. Oh, what was his name? Mathematician, free will. It was with the law of large numbers, maybe. It was a Veritasium video. I'm trying to find it. This was the video. I just want to find the dude's name and look up the dude. Just an analytic philosopher? I guess so. Seem nice, but math is scary. That's fair, Lopta. I do play games too, and I also sometimes go on rants about just not rants, but just like run my mouth about random stuff sometimes. Uh, Dang it, the other person was Markov, the person who thought he did it. Wait, John Conway has a free will theorem? Spinoza, maybe? Tico, no. Huh. Okay, this is also interesting, but okay, let me look up Markov. Because Markov had a feud with this dude, and Markov basically showed the dude's argument was terrible about uh free will. So Markov was a mega atheist. Not just a regular atheist. Oh. No, I don't think that's that. Damn it. It's gonna bother me. History. There we go. Pavel Nekrasov. Where is this gonna talk about it? Free. Ah, doesn't. You dated his sister? This guy? Color code? That I think that's a fantastic idea. Alrighty. Nekrasov. Nekrasov. Oh, I guess there's this person has the same name. Free will. Oh, playlist is looping. 1 second. Let me switch it up. What is this song? I must have liked it. Oh yeah, this song. Ne Nekrasov asserted for any sample drawn from a system with interdependent. What a terrible word. Interdependent. Isn't that just dependent? Interdependent. Yeah, okay, just say dependent. Why would you add 2 more syllables to a perfectly fine word? Of 2 or more people or things. Dependent is... Oh, okay. I guess that's fair. Dependent is just unidirectional? Okay. You got me. For any sample drawn from a system with interdependent observations, there is no way to define its long-term behavior, that the only near independence of real-world events makes statistical analysis of phenomena such as crop yields or deaths even possible. Nekrasov went on to claim that human action is therefore inherently unknowable, necessitating free will. Yeah, okay. That's the argument that I was thinking of. That wasn't the exact argument as it was presented in the video. Atreides nuts? I'm probably pronouncing that wrong. That sounds like the name of a star. Atreides nuts? Either way, I love that name. Or maybe like an ancient Greek. Nekrasov's assertion is the logical inverse of the famous statistical law of large numbers. That's what... Yeah, okay, yeah. Which states that if observations are independent, the average of the observations will approach a unique, stable, fixed point. Pronunciation is great. Oh, it's a Dune thing? Oh, I really need to watch Dune / read it. Oh, okay. Whatever. I still love a good D's nuts joke. We need to return to D's nuts jokes. Go back to my Welsh lesson. All right. Good luck, Lopta. Okay. I have too many tabs open. Make these nuts great again. God damn it. Oh, that's funny. I don't know why I find these nuts jokes so funny. They're just so stupid that they come back around to being funny. What generation is responsible for these nuts? Even just that question makes me laugh. But that's a good question. I think of like the streamer Ninja when I think of these nuts jokes. Isn't he the one who like popularized like Ligma and Sugma? I don't know how old is Ninja. Or wait, maybe people are saying that about Ninja. Born in 91. Really? Oh. I didn't realize it was like that old. I'd never heard like a decent nuts jokes like the Ligma and Sigma ones until about like that 2018 time. Ooh. I always like looking at people's signatures on the Wikipedia page. What is the extra stuff down there? What's his actual name? Richard Tyler Blevins. Huh. ...2007 Australian punk band name. Right here? I don't know how you would say that. Or maybe you mean somewhere else. um, I'm kind of stuck in this problem right now anyway. I've got something I don't know how to deal with. Could look for something else to do instead. Hmm. Nos da. I don't know what that means, but I see you waving, and you did say you're gonna go back to your Welsh lessons. I assume that's some form of goodbye. So if that is a good goodbye, Lofted, then I'll see you later. Hey Shivam, hope you're doing well. Um, what else? I could pull something else from this book, or I could go for another book entirely. Was anything pending my Discord, right? Let me just... I don't think so. I could try the same problem, but with Laplace. No, I'm gonna get lost if I try to do the Laplace part. I don't think I've pulled off a single Laplace question successfully. I think I've done one Fourier transform. The integrals I end up with, I don't know how to deal with them. You know what I could do? I could look, where did I save them? The book's explanations I've sometimes been struggling with. I could look, where is it? Oh my god. Here it is. Just pull it up quickly. I had this other book that I could look through too. Where do they cover this? To relearn all the Fourier SNA transforms, I kind of lost it. And that's still an accomplishment to have learned it in the first place. I sort of learned it when I did my undergrad degree, like 7 years ago. Like I was like kind of barely introduced to them, but I never had to do them on this level. Page 77 looks promising. Z, not A. I don't think I've heard of those single letter transforms. Go my table of Fourier transforms? That's cheating. Okay, heat equation. What is an S transform? Oh. Short time Fourier transform. Is it also Laplace? Well, Z transform. Oh, discrete time equivalent of the Laplace transform. Nice. Okay. Yeah, this sounds like a really important thing. There's a pretty cool story behind the fast Fourier transform, which is a hugely important transform. That basically involved anytime you have like a signal. Electrical and engineering signals and system classes. That okay? Yeah, I was thinking that you're probably an electrical engineer. Yeah, Zach, the sort of the fast Fourier transform. The mathematician who discovered it, I think in the 60s, was literally like bored in a meeting with JFK and a bunch of other like scientists and mathematicians who were trying to do something. They wanted to find a way to, oh my god, I'm quoting a Veritasium video. There's an effort to ban nuclear weapon testing after World War II. that countries were actually like pretty on board with if they could verify that all the other countries aren't testing nuclear weapons underground where it was very hard to detect. And the ban that eventually went through didn't apply to underground testing, which is why there's a whole bunch of it later on, because they just couldn't find a way to detect it. But if they had the fast Fourier transform, they would have been able to do it. They just realized too late, and then the political will was gone. But oh, okay. And as happens with math, Gauss discovered it first. People just didn't realize it. Yeah, but the people who just rediscovered it, one was literally in a meeting with JFK on this topic, and he was bored and just like doodling on his paper basically, and figured this out. I don't remember if it was Cooley or if it was Tukey who was doing that, but I saw it was funny. Like you're literally in a meeting with the president at the time. You're just spacing out. Oh God. My best rendition of Gauss. Let's get a reference picture. This is like the classic one people use for Gauss, right? Yeah, okay, this will... It's not gonna work, but you said my best rendition of Gauss, which is thankfully relative. That's a... Oh no, that's gray. That's not white. Oh man, there's like so many options for shades of white. Okay, we'll use that white. Yeah, Gauss's signature it is awesome. Let me show. I've seen it before. This is his signature. Imagine trying to do the signature if you just like paid for something with your credit card and they hand you the receipt to sign. I'm not doing that. So they're calling it the best algorithm of the century? Yeah. A prominent mathematician called it the most important algorithm of our lifetimes. Oh my God, what's his name? Strang. Gilbert Strang. It's gonna be bad. I haven't drawn anything that's gonna be bad. You simply ask for your signature when paying the bill at a restaurant. Yeah, it started to go in the direction of not. But if you pay, anytime you pay for something with your credit card, some places ask you for your signature, some don't. I don't know what the pattern is, to be honest. It probably depends on what technology they have there. We never learned FFT, so someone familiar with DFT. Okay. Yeah, as I understand it, the fast Fourier transform is just the DFT, but you find shortcuts in the calculations. I never learned it either, though. Chip versus swipe? Maybe, yeah. I definitely have had to do it for, like, even when I tap, though, at some places. You don't have that in Canada? Oh, interesting. It's definitely, like, it's becoming less common here, but it's still, like, frequent enough. Oh, this is gonna be terrible. You know, I never noticed his hat. It blends in with the background. I was about to say I can't decide if I like it or not, but no, I actually I can decide, and I don't like his hat. Okay. That hat fucks. I'm sorry. I it's like someone deflated a chef's hat. That's why I don't like it. We are gonna start with the hat. He's like he's about to see the ghost of mathematics future. No, he does look like I've been in your screen. Oh my god. That that's actually such a good comparison. Oh my god. Like this one I think is the closest. Maybe this one. I don't know how I never noticed that. He definitely has Scrooge vibes. Although in this portrait, at least he looks a lot nicer. Where it's some of my friends like to sign those with James Bond when he travels in the US. Yeah, I mean, no one really checks it. You're sort of right. And some things about why no signatures are needed. At least that's often. Did I sneak in a Sean Connery accent? I didn't. Sometimes I do it on purpose. That time it must have been an accident if I did it then. Oh, the James Bond. Oh. I remember being a good citizen, and the first credit card I got, I actually did sign the back of it. I don't think I ever did it again though. Marley would sit around the office all day calculating interest on accounts. Scrooge would not let him burn coal in the furnace for heat. Probably working. Wait. Oh, is there a different Bob Marley? I was equally confused, Zach. Is that a character? Oh, Jacob Marley? Oh. It's like that'd be a hell of a crossover. Bob Marley in a Christmas Carol. You know, I think Ebenezer Scrooge would benefit from listening to Bob Marley's music. But yeah, I guess they're going away because we have the chips now. Which I don't understand how are the chips harder to replicate? I don't understand like how they're actually more secure than the old swipe. A one-time only. Oh, that's wild. How do you make that with a chip? Wow. Okay. Yeah, it's like the car doesn't have electricity in it, so it could be like an RFID thing where it gets electricity from the signal, but like how the hell do you make it change the code each time? Okay. We're going on a rabbit hole. How do the chips and credit cards work? Are we trusting random people on Reddit? Let's go to Wikipedia. Tiny Tim's dad brought Bob Cratchit. Oh, okay, okay. NFC chips can do very limited logic. Okay. Okay, fine. Let's look at Reddit. The chip is a computer. How? Okay, but then how does the tap work? The tap must be like the RFID thing. How do the does the tap? Sure, contactless payment. Let's look at this random website. Wait, really? Do I not know what an EMV chip is? No, it is that. What? They've been around since the 90s? I don't think I ever saw one until like the 2010s. This is not the timeline I had in my head. Probably chocolate mints? Oh, hey, near field, that's what it stands for. Okay. It is RFID. Aha. An induction. That's still wild to me that it can do actual computations like that. I always imagined RFID as like only doing simple things. Hmm. Tend to radiate though? Uh well, okay, yeah, they do say principles. So it's probably not actual RF. But I just meant like the thing that I'm familiar with is like RFID chips where they are like computer chips, but they don't have any power source for themselves. They just get powered when you bring them close to like a scanner or something that gives them power for a minute. And so it sounds like this is the same thing, but not radio frequency. Yeah, that's fair. Oh shoot, we still have to. I should work on Gauss while I run my mouth. Uh, what, dude? Who's? That's a sideburn. Okay. Okay. Yeah. Yeah. Okay. He just has like SpongeBob level of sideburns in that one episode. I read a funny story about Grothendieck going in front of a judge for housing a Jewish student in a hippie camp. So he's expired like 15 days ago. Because of some old anti-Semitism law that was considered a crime, Grothendieck represented himself in court, told Moore plead really hard to the judge. He wanted to have the maximal sentence. Really? Trying to get in salty spittoon? Was it that episode? I think he was trying to be a man for some reason. Or like look tougher. SpongeBob's hairiest moments. I need the context. Oh, there we go. It's when they go to Grandma's house. Who wrote all these synopses for all these SpongeBob episodes? Oh yeah, because his grandma makes him feel childish. Yeah. Okay. Slur whoever they are. It's also a mess in the court. I actually was just reading Grothendieck's Wikipedia page like yesterday, just out of curiosity. He had a crazy life, which I knew, but I was reading because I didn't know like the extent to how crazy it was. Also fun. Thank you for still being here. Holy crap. Uh, I'm looking through my color palette right now. I don't have much of a color that matches his skin color. He's gonna be a little orange. Eh, yeah. Green bean casserole in the meantime? Oh, I mean, yeah, I didn't expect you to be here like continuously or whatever, but like, thank you for like coming back, I guess. Green bean casserole sounds phenomenal. Yeah, I do like how Gauss was given a little like eyebrow raise. It's like how you doing? His eyes just kind of look black, so I'm gonna make them black. Actually, I guess they're probably brown, right? We're gonna make him brown. Where is brown? Okay. Gotta get that big old honking nose. That Ebenezer Scrooge nose. There we go. Okay. And then it's a little too big. You know, it's so far it's coming out a lot better than I would have expected. By my standards, this is actually not bad so far. Blanch the beans and bacon grease. Oh my god. That does sound phenomenal. When he got his field medal, he's supposed to get into Congress in Russia. He was really not into that. Dad? His dad was convicted twice to death by both Russian Tsar and the Illich regime? Oh, wow. I thought he rejected it because of something involving, like he's a pacifist and, he didn't like that the math he worked on for that was being used by the military or funded by the military in some way. The HIES, French institution where he worked. Okay. I thought it was for some work he did at the HIES, but I might be getting it mixed up. I think I get really annoyed if I had to wear these little like, those colors are just way too flappy. I'm not going to do his entire, like, clothing get up here, so I'm going to, like, simplify it a bit, but, I'm feeling my drawing skills right now. The frills, though, Don. The frills. It's true, Zach. We need the frills. Pivot, how are you supposed to do anything if you're distracted by streaming? That's a good question. I'm definitely not as productive when I stream, but I have a lot more fun. Ooh, Twitch didn't like that one color cone. The Automod didn't. At least 70 lapels sat flat. Yeah, exactly fun. His dad was really something else. I don't know what you're doing at 14 years old. His dad was already trying to assassinate the Russian Tsar. Yeah, and Grothendieck tried to assassinate Hitler. Which is kind of wild. Big balls maneuver, yeah. Like, well, I think there's a dude who went to North Korea with just like a machete or something. What he was trying to do his own assassination attempt on Kim Jong Il or Un. I don't know if it's actually true or not. That was just something like I heard on the internet. But like, some people just feel like they have what it takes. I guess I don't know. I mean, I'm putting way more effort in this than I probably should be. We got his field medic, he ended up selling it right away. Oh, I didn't realize that he actually received it. Eventually. It's funny. I wonder who has it now. Then Grumpdig managed to escape from his. Yeah, I read that Territar. Pretty wild. Some people's symptom clusters overlap assassinating world leaders. It's a thing. You know, I guess so. Someone else went to Russia for him. Oh, okay. All right, this might be my best rendition of Gauss right here. Should we do a bit more justice to his hat? I don't know. I feel like I'm gonna mess it up. His deflated chef's hat. Oh, it's the song. Ah, where's Fembox? Okay, I'm calling that a drawing. Posted in the Discord. I should do my signature in Gauss's style. I don't. It's really elaborate. I don't know. It's only three letters. My name. I I don't think I can do that, but I will say that in like elementary school and middle school, when I wrote my name on like the whiteboard at class, like or just like wherever, I would write like Don, but with like a pi instead of an N. So you know, some math teacher before I even knew that I liked math. Part of delusions of grandeur. Yeah, I guess it makes sense. Fun. I don't want to do the heat equation. I think I can do the heat equation. Oh, that's what I remember. Okay. Probably an hour ago now. I was gonna look through this. Suppose to rebrand your name to DAW 3? Oh my god. That's hilarious. Oh my god. So wait. If Euler's number is 2.71 dot dot dot, then is DO 2.71 dot 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 the same thing as saying like a dough? When Grothner D turned into weird stuff, he was watching class outside in the grass in a picnic. It's pretty good at pissing off everyone. Teaching class outside. Oh, yeah, yeah. No worries, color code. Hell, this song already sucks. I'll go for a little longer, though. Maybe it redeems itself. Exercise for the reader. There we go. Evergreen State? I don't know. What is so special about Euler's number? Great question. Euler's number is kind of weird because it just kind of pops up. And then we kind of started using it at anytime we need an exponential. So the thing that's unique about Euler's number is yeah, and I think about like the limit definition. There's a couple different things that we could start with here for Euler's number. So if you let me start with let's start with like a question about finance, because this will turn into Euler's number. If you start with say $1,000, keep the numbers smaller, and it compounds 5% annually. Sorry, and you get, I guess, the interest. I forget the exact like right term, but something like that. They're 5 years, 10 years, a very long time. It came from oh wait, I'm doing this off the top of my head, so I'm gonna do this slightly wrong. Yeah, where's X when you need it? You know, I should actually look up an explanation of this. Because if I try to refigure it out here, I'm gonna mess it up. Yeah, that's right. You make the time, like you would start with 1 year and then 6 months and then 1 month. Okay, so I need to rephrase the question. So instead, we're just gonna do. I guess we can still say it's compounding. Okay, so instead we're gonna have 100% compounding interest annually. How much money do you have after 1 year? What if you cut the interest rate in half, but compounded it twice per year? And so on like that. Like cut it in thirds, but 3 times a year, in fourths, but 4 times a year. How do you figure out how much money you'll have under these different, like, kind of schemes, I guess? So in the first situation, where it's just 100% interest after 1 year, you have $1,000 and you multiply it by 1 plus 100%. I hope I'm doing this right. But 100% is just the same thing as 1. So you end up doing 1,000 times 2 is 2,000, which hopefully checks out with you. In the second scenario, compounding twice per year, but half the rate, you would do 1,000 times 1 plus 50% twice. N times n in the exponent, 3,000. It might end up being with 3,000. No, I think it's not. I think this is it's gonna be 1,500, and then half that again. 225. I think that's what the website said too. Yeah, it's gonna end up being I think 225. And so this would be even better done in a spreadsheet, but the pattern would continue like it would keep on going on. Is equal to whatever. It's not important. I'm just trying to build up the pattern here of the stuff in parentheses. And so the amount that we start with, like we don't really care about that. We can always plug them at the very end. The thing to really pay attention to is like what's happening here. And so we can kind of make this pattern a bit more general by saying it's 1 plus I, the like interest in this situation, divided by m. I'm just following with color cones formula here, which is the number of times you compound it. to the power of n times m. But here, n would be the number of years. We're just doing 1 year though. So I'm gonna chop that n off. Oh yeah, Zach, a person in the YouTube chat asked what's so special about E, and so I remember vividly you doing this explanation in a spreadsheet a long time ago, and so I was trying to like recreate that, but not as good. And so the question that a mathematician might ask, or even just someone who's curious about it, is what happens if you compound, like what happens for like a really large number of, if you compound it a really large number of times per year. And so mathematically we would say that we were interested in the limit as m goes to infinity of this thing here. And as it turns out, you actually get 2.71 something, which we call E. So even though compounding more times per year, it does like increase your money. We went from 2000 to 22, 25, and we would get more and more each time we increase. It does level off. Like you're not going to get another $200, or you're not going to get another $225 the next time you compound. It'll still go up, just not as much. And so that's kind of like the curiosity that it's like a curious thing where it kind of like converges towards something. It doesn't just keep on increasing. It's that's a way that it can kind of like organically come up in things. I'm not really doing this explanation justice here, but that's this is one way that E like just kind of appears. In fact, we can define E by this very limit here. But the next thing that makes it so special is what Teratar just put, which is another way you can actually define E, as far as I know, which is you can define E as the function that satisfies this differential equation. Like it's the thing that is equal to its own derivative. I hope you know calculus for this part. And actually, if you don't know what a limit is, let me know. If you don't know what a derivative is, well, let me know, I guess. But I hope you do, because this will make more sense if you do. So e to the x, or e to the t, I'll say e to the x, is the function that satisfies that differential equation, and that's a really cool property. It makes E come up all the time in differential equations, because if you instead had something like y prime equals 2 times y, sure, it's not the exact same situation, but you can be pretty dang sure it's going to involve some version of E. And so whenever you have like a function that's a derivative involved with each other, E usually is lurking somewhere in the background, if not in the foreground. Does it imply that the rate of increase decreases with time? If so, then the slope of the tangent shall decrease to increase with x. That's a good question. I'm just trying to parse through it. So we need to say with what? So the function e to the x itself does not do that, because it's an exponential function. It looks like that. It definitely doesn't like level off as you increase x. But like up here with this interest rate conversation, the thing that's leveling off is actually, you know what I've never done before? Aha. So this function does do the exact thing that you're saying. Ignore the negative part. We're not interested in that. This function that we got from kind of like the compound interest, that levels off. The further to the right you go, the closer you get to 2.71 whatever. And so you're kind of getting at the idea of convergence. This curve here levels off, and it doesn't shoot up to infinity. It's never going to pass above this blue line here, no matter how far to the right you go. Tell me, you'll tell Labrador Retriever both be stoked for you. It's gonna go over our heads. Oh, what they did in the 1700s and in 25, we cannot manage to get continuous taxation. So, so yeah, if you were to take the derivative of this, you would find that it's going to approach 0 as x goes to infinity, I guess. But yeah, fun. I'm not explaining something to you that you already know, but we're talking about, it's called E Euler's number. It's a number that's like pi, where it goes on forever without a pattern, but it comes up in like slightly different contexts. And so Hibbit and YouTube was just asking about like, why is it important? Once again, I have a million tabs open. Oh, Zach, I didn't get your comment. I did complete the drawing of Gauss. You might have stepped out when I finished it, but this is how it ended up. All right. This might be a nice place to call it for the day. Unless I get a further question from someone in chat. I do want to go through this other explanation of the heat equation. That might be an off-stream activity. It doesn't look like it's explaining a lot more than the textbook does. The other one does. Yeah. I'll go through this another time. So yeah, people are here on YouTube. Hibbit, Tertar, thanks for being here. I don't know when I'll be back, but I'll be back eventually. On Twitch, we'll look for a raid. See ya, YouTube.